This talk has had a lot of involvement from a lot of people. They're all up there. Hope you read it. Look, this talk builds on some work we did over the last few years. It's involved a lot of people across government developing these report cards. These report cards are all publicly available on EnviroData. Essentially, we did an audit of environmental information the government was holding, or anybody was holding that we could get access to report on the condition of natural resources across the state. I encourage you to turn up to Craig Meakin's talk tomorrow. Craig's going to be giving a good deal of insight into these report cards, but explicitly this project I'm talking about this afternoon builds on one of the report cards and some of the gaps that were identified in it, which these report cards quite nicely show. They have a section dedicated to the trend, the current condition or the latest condition of the resource, and a section on the reliability of the information. That was made up. One of the components that is used to derive that reliability is when was the last time these data were collected. We know our native vegetation information that we hold in Juna is really great. It's fit for purpose. I couldn't count the number of dollars put into that when it was done, but it has been a fantastic resource. But what we know is that it's very expensive to update it, and so it hasn't been updated for a while, or it's not maintained to the quality that it was originally developed as. So this project was developed to build on that, and essentially what we've developed in this project is a series of land cover models. So for the bounds of this project are the whole state. The bottom dot point says there that Victoria has done it with us using the same methods and exactly the same input data and the same modelling approach. So South Australia and Victoria have both there are these data sets that will be very shortly available for South Australia and Victoria. They're continuous models of every land cover feature. So the land cover features might be a particular vegetation type, or they could be something quite broad like all native vegetation. But importantly, just to get this in, I've got a couple of examples in a second, that these are continuous models for each feature. I'll explain what that is. The outputs also include error models of each feature as well. So from each, if we were to just take each of those features and take just the maximum likelihood for a given location, we can then build a maximum likelihood map, which is more what you're used to seeing as a native vegetation layer for a particular state or a region or a project level or whatever you're looking at doing. Importantly, this method allowed for a repeatable approach. It's based on Landsat data, so the scale's 25, 30 metres. And that's the input data at 25 to 30 metres, and so that's the scale the model's built at. Is for South Australia and Victoria, they're 25 to 30 metre pixels. It goes back to 1985, which is the extent of the available Landsat, or the extent of the usable Landsat data for this project. And from that period, we've broken it into 5-year periods, and so there are 6 epochs. So we'll be able to look at change from then up till now, and in the future be able to keep building on this. 25 metre resolution next. So the models are predictive spatial models. Essentially this is taking a view of how the satellite sees a given vegetation feature. So the satellite needs to be able to discern this feature from something else to be able to be good at predicting what that feature is, and then make a prediction of where that feature occurs across the landscape. We then, if we can get a good signal from the satellite and we can get a good relationship between where we know that feature is and how the satellite sees it, we can then be fairly confident that our predictions are going to be quite accurate. So we apply our predictions to the rest of the Landsat data and come up with a map of what vegetation distribution looks like for the state. In order to train the model, we need to be able to tell it that at a particular location, this feature occurs there. So the model has 50,000 pixels of training data from South Australia and Victoria. They're either from aerial photo interpretation or from mapping that Juna has that it's extremely confident in, or mapping that anybody has that we could get access to in order to be able to train this model. So those were the initial set of training data. We can build on that at any time, and indeed that's been already out of some of the model drafts. We've identified places where we'll need to be doing that. The training data needed to cover temporal and spatial variation of those features. So we needed to know not just what it looked like when it was perfect, but also at the extremes of its range, so that we could tell the model that some of these more degraded or some of the feature in its drier areas might not look the same as where it gets a bit more rain. So the model needed to be trained with essentially, if you can think of it the way the satellite would see it, different views of the quality of that vegetation. And most of the features needed to be a little bit bigger than 25 metres. That wasn't the case in every case, but it certainly made the training of the model a lot easier. So 25 metres being the scale that the Landsat satellites take a picture of the Earth every week or two. So the model used every Landsat pixel, every Landsat photograph of any pixel that was cloud-free and cloud shadow-free between now and 1985. Landsat records light in 6 bands, so you can see there the sun, it's passive remote sensing, so the sun shines down, plants look different colours to the satellites when that light shines back up to them. It's a pretty simple formula. The cloud shadow free is very important because plants look different when they're under a cloud shadow. They look quite dark and they're not visible when they're under a cloud. The model inputs are split by season, and then we took quartiles of those and summarised those into the 5-year epochs. We took a bunch of kind of standard remote sensing derived indices in addition to those, but they're the model inputs. These are some more model inputs, also some radar data that were freely available from some of the more recent inputs, more recent epochs. Those were used as inputs to the model as well, really to discern between buildings that had green roofs, paddocks that were green, just to be able to help us pick out trees a little bit easier. And also Geoscience has this data layer here called Water Observation from Space, which is an amazing data layer to pick out wetlands or pick out wet areas. So when I said it's a continuous prediction of a given vegetation feature, this is one here. So this particular feature that we've got here, I've written him out down here, it's a nested feature, so it's a bunch of actual features. You can see here it includes mangroves and mallee and any tree in the area of the top of the Gulf. So what we've got in this layer here is where the model is confident that it's making a prediction. It shines up red, so you can see the mangroves on the edges, a few little bits of northern New York that are left over here, and some of the other areas up the top of the Gulf. Where it's not so confident, it shades it up blue. So fortunately, there are no trees coming up in the middle of the ocean, which is a good thing. So the model's having a go, and so if you can understand that for every vegetation feature, there is a layer like that. I'll give you one other example, just in case you're not clear on that. Here's another one, which is all native vegetation features around Mclaren Vale. And again, you can see the blue area is where it's, there's some urban areas in the middle there. There's a little conservation park down here. So any of the model is built like this. It's not just a single model, it's not just a single layer. And this essentially allows a whole lot of different analyses that may not be possible on a map that's just a static feature of maximum likelihood. I mentioned before that most of the features had to be bigger than 25 metres. That wasn't the case. Because we had so many people in this project, and it was scoped with so many regional staff in mind and their needs, and they're actually paying for it. A lot of them wanted to be able to do really fine-scale analyses that pushed what we could do with Landsat. And one of them was to do a census of paddock trees, and another one was following the 2007 bushfires when South Australia adopted some of the clearance laws from Victoria, and we allowed clearance around structures a little bit without having to seek approval and without that having to be accounted for. People wanted to be able to say, how did those policies and how did that fine-scale clearance impact on our native vegetation extent? So with this paddock tree example here, I don't think I'm the first to call them living fossils, but I certainly understand why they are. I took this picture last weekend, and you can see that down the southeast, these trees are not going to be there for long. Not great recruitment in that area either. So the model in this case, this is an early version of the model, just to make sure that we could pick up paddock trees. Landsat data typically aren't used for this. In this model, we essentially train the model to say, look, if you're seeing out in the middle of a paddock, if you're seeing a perennially green feature with brown all around it, then call that a paddock tree. You can see that they're not, if we take this guy here for example, because it's clipped over a couple of pixels, it's getting that algorithm's working and telling it that there is a greater extent of that paddock tree than what it actually is. And so we're certainly overestimating the cover of paddock trees, but this will fix itself in time, and we'll be able to, specifically for that really fine scale feature, we'll be able to clarify, or fix that one up with no trouble at all. The second map here, this next lot of maps is what I'd talk about, where we mung all of those continuous models together and we just take the maximum likelihood. So for each given 25 metre pixel, we look at who wins, which vegetation feature has the highest likelihood prediction, and then we can make a map which is more like the typical vegetation layers that you're used to seeing. So the legend over here shows each of the, or not all of them, but some of the standard vegetation layers which are in this. You'll see we've been able to break this up a little bit more than what remote, 2 minutes, than what remote sensing projects often do. And so I'm going to skip through here and show you the growth of blue gums in the southeast. You can see Narracourt just up there. So we'll see the growth of blue gums since 1985, shining up brown in this area down here. So we'll chop them down and we'll put them back again. Mclaren Vale, there's a couple of really interesting things here. The top circle shows the expansion of a quarry. Over here we've got some blue gums again, and down here we've got an increasing urban area over here. Don't worry too much about seagrass. We are using the model to make some predictions about seagrass as well, but just ignore that left-hand side at the moment. We're doing a bit of work on that right now. So we'll flick through from 1985. There goes the quarry, blue gums over there, and a little bit more urban expansion. Let's take them out, put them back in again. There we go. So what we're looking for this is projects that really engage the community in the use of this model. This is really an advertisement. This model is going to be made freely available in Juna's usual ways. We'll get to that in a second actually. We're looking for projects that show the value of native vegetation, and we're looking for people to use this as inputs, and we're going to really help to facilitate that wherever we can. We want to show any of those projects there. But really, what else have we got here? So all models will be made available for free. This is part of the government's commitment under open data, and that's why we did this project, was to be able to put this out as something that would show change and also as input data for anyone else's models, which I'm sure, well, I know there are already many uses coming up for these data. There is quite a deal of administrative work within Juna to get these models out. They're huge data sets. Each of those continuous variables and its associated error model is maybe 100 gig in itself. So they'll all be available soon. We're not sure how we'll do that. There are many big files, so the model's not yet finalised. We've gone through our second last draft, and the last one will be delivered within a couple of months. It's been very expensive. It's had a hell of a lot of collaborators. All interim boards, several SA government agencies have put money into it. The Victorian government and Commonwealth agencies have also put money into it, and that's been one of the strengths of this project, is it's delivered at both a state level and at a regional level. So we had people in the room telling us, no, if it's not going to deliver at to my project so I can assess my investments, then I'm not putting my money in. And that really gave it a reality check of what we were doing. We scoped it with all of these people, and the modellers who have been doing most of this work for us had regular input into this process as well. It certainly, we hope, will have enduring outputs and will provide a repeatable method, and the Commonwealth Federal Department may apply this nationally. That's certainly been something we've been pushing for since the start. What are you doing? The end.
Thanks, Brad.